Hi everyone. Thank you for joining me for today's discussion on light and how we use light, specifically reflected light microscopy, in mineral identification. My name is Daniel Gregory and I'm a professor in economic geology at the University of Toronto and will help guide you through this. So over the course of this discussion, we'll go over what light is, and then specifically what polarized light is. And then we'll talk a bit about how light interacts with materials and how we use these interactions to help identify the minerals. And then we'll go through some videos where you will examine the videos and try and determine the properties that are being shown in the videos and use that to identify the given minerals shown in the videos. Light is special. And it's special because it has both properties of a particle and properties of a wave. So if we think about it as behaving as a particle, this particle is a package of energy that has energy but no mass. And we call each of these packages photons. And the brightness of the light source is related to the number of photons it produces. For most of this discussion, though, it's a little bit easier to think of it as a wave. So when it behaves as a wave, or when we're describing it as a wave, it has both a magnetic and electric component, which is why we also refer to light as being electromagnetic radiation. And this can be visualized in this bottom diagram here, where we have a magnetic field that is oscillating in a wave like this, and an electrical field which is oscillating as a wave in this direction. So I'm going to go through some terminology now. We'll be talking about wavelengths. So this is the distance of one part of the peak of the wave to another peak of the wave. And it'd be any part along that wave when it hits the same part again. And if we have many waves to group together, this is called a ray. So this diagram here is kind of showing the ray of these many different waves of light going in the same direction. And the wave front is the part where the wave, or where all of these different waves of light has their same point. So at the peak of each of these waves here, that's the wavefront. And in the previous slide, I referred to light as electromagnetic radiation, and depending on the length of the waves is the type of light we have. So visible light is in this very small area here. And this gives us all our colors. So the longer wavelength is red, and then the shorter wavelength is purple. But this is only a small part of that electromagnetic spectrum. If we go down to radio waves, our waves of light can be measured on the order of kilometers, whereas when we go to gamma rays, they're all extremely, extremely small. And we use in all parts of our life, all parts of the parts of the spectrum. So we can use gamma rays or X-rays, X-rays more in imaging through things because they penetrate further, whereas cell phones and TV stations utilize these longer wavelengths, which are much less likely to cause damage to people. Now, one of the things we're going to be talking about today is polarized light versus unpolarized. So our normal beam of light is going to have these waves of light going in all kind of directions around the beam. And we can put it through a film that only allows one of these waves through. And this can be more useful for us when we're talking about its interactions with matter and how we can determine different properties of that matter using the light. We'll go into that in a little bit more detail. But one of the applications for this that you may be familiar with is polarized sunglasses. So we often wear these this sort of sunglass if we want to avoid glare. So if you're a fly fisherman, you might use them to avoid the glare from um, from the creek that you're fishing in, or if you're a skier, you might wear them to avoid the glare from the ski hill and the snow reflecting off. And the way that works is we're only letting through one wave, and we can depending on how we arrange our sunglasses, we can make it so we're only letting through the vertical wave. And since when it's glare that we're trying to avoid, most of that comes in horizontal. So if we so most of the light will be coming in kind of in this direction, and it gets stopped by this film. And this is called polarized light. We're only letting one one direction of the light through. All right, so now I'm going to touch a little bit on the interaction of light with matter. So the velocity of light is different when it goes through different materials. So you may remember the famous constant of the speed of light, which is about 300,000 kilometers per second. So that's able to go around the circumference of the Earth 7.5 times in 1 second, just to put that into perspective. But when it goes through different materials, that material will slow it down a little bit. So depending on the chemistry and how those different materials are made up, it will change the speed of the light depending on the material it's going through. So some materials, the speed that the light can go through them is the same in any direction, but other materials, depending on how their atoms are arranged, it'll change the speed on the different angles that the light is hitting it. So an example of a material where the light goes the same speed would be pyrite, and this is because it has a structure that is kind of the same from every angle. Now, an example of one where the speed at which the light is different is the mineral covellite, and this is because you can see kind of if you go in this direction, it's going to be hitting different atoms than if we go at this direction. So depending on the angle at which the light is going, is impacting it and is going to interact with the material, that will also change it, like in this layer here. So because the different angles that you impact the light on are interacting with different parts of the molecules, it's going to have a different reaction. And this is the mineral covellite in hand sample because I couldn't fit it on the slide earlier. All right, so just going back, polarized light versus unpolarized light. Our unpolarized light is all around the beam of light. We have the waves kind of infinitely around, and polarized light, it just allows it to go in one direction. When light goes into a substance, the polarized light will split into two rays with different orientations. And if the material is not electrically uniform, like our covellite here, then these rays will go through the material at different speeds due to the arrangement of the atoms and kind of the direction of those waves. And the strength of each ray will be determined by the orientation of the crystal. And this means that as the crystal is rotated, then the mineral color is going to change. So this is what occurs with covellite here, whereas with our minerals like pyrite, where they're electrically uniform, the rays are going to go through at the same time or at the same speed, so there's going to be no color change as we rotate the mineral. And this is sort of an example of that, where we have calcite here. And you can see that the image beneath it has been duplicated. And this is because we have those rays have been split, and one goes through faster and one goes through at a slower rate. So we have different instances of refraction. So kind of what we're seeing here with these two lines, or the word calcite being repeated here, is the slow and the fast wave of light. And one's slow and one's fast because of the speed at which they can go through the material due to their orientation. All right, so now we're going to go on and see how this can be used in these properties can be used in geology, and how we can use these interactions of light and materials to identify different minerals. And this is a budding geologist here. All right, so I'm going to play a video here of pyrite, and we're going to see whether, as the stage is rotated, we're going to see whether, as the stage is rotated, there's any change in color. So pyrite is this yellow mineral here within the circle, and you can see it's fairly uniform right now. We're going to start rotating the stage, and it is clearly not changing. So this is just kind of showing how under a microscope our pyrite's going to look, and if it was not electronically uniform, it would be changing colors as we rotate this stage. All right, now we're going to move on to look at covellite. And now covellite was our example where now we can see that there's a number of different colors here, from this bright blue here to these lighter blues here. And as we rotate the stage, let's just follow this. You can see this is going from light blue to dark blue. And then let's look at this one here. It's now dark blue, and it's going through and it's lighter blue. So this is because we're changing the orientation of the crystal. And because we're changing the orientation, we're changing whether it's the fast wave or the slow wave that is shining through. All right, so we can get additional information in addition to this. So what we just saw there with the pyrite and the covellite is that we can determine whether something is bireflectant or not. So if it changes colors as we rotate the stage, then it's bireflectant, and depending on those two colors that we get from that, we can use that for mineral identification. And the case with pyrite, which is not bireflectant, we can see that the fact that it's not bireflectant is one of the properties of pyrite, can be used to identify it. Now the other information we can get is if we put a second polarizing film at 90 degrees. So we have our first one, that is our plane polarized light, that is done before it gets to the sample. And if we put another one at 90 degrees after the light leaves the sample, that can give us more information. So I'll just define these two terms quick. So there's isotropic, and this means that this is an isotropic mineral has the light that leaves the polarizer being the same as the light that enters the upper polarizer. So the sample doesn't really change the orientation of the light. And this basically means that when we put something in cross polars, so we put the second polarizer on, it ends up just being black or dark. Whereas anisotropic minerals, the light is only sometimes at the same direction as the original light. So some light is allowed through by the upper polarizer. And both whether that occurs and what color that occurs is also diagnostic of the different minerals. So we're going to have a look at pyrite in cross polars. So here's our pyrite before. This is just in reflected light. And just let it rotate it for a second, and then we'll see it in cross polars. Here it is in cross polars, and you can see this is our pyrite crystal here, and we're rotating it again. It's completely dark, therefore it is isotropic, and that is a diagnostic property of the pyrite. Now we're going to have a look at covalite, and go through. So again, here it is in plain polarized light, and we can see it's rotating. Now we're switching to cross polars. And this time we can see these bright kind of yellow orange crystals. And you can see as you rotate it, they're getting more yellow or orange, and then eventually going dark. And then as we continue to rotate, it keeps coming up. So this is an example of an anisotropic mineral, and both the color of the anisotropy and the fact that it is anisotropic is indicative of this mineral, and we can use it to help us identify it. All right, so now try and see if you can make these observations for the next two videos. So what I want you to do is write down the mineral color in plain polarized light, and then whether it's bireflectant, and if so, what two colors do we see, and then whether it's anisotropic, and if so, what colors you see. So just as a reminder, bireflectant, the colors change when the stage is rotated in plain polarized light. And anisotropic colors are there, so it's not just dark, and change when the stage is rotated in cross polars. Okay, here we are in cross polarized light. All right, now here's our second sample, and we're going to do the same. So again, we want the mineral color, whether it's bireflectant, so what colors do we see, whether it's anisotropic, and if so, what colors do you see? And here we are in cross polarized light. All right. Now we'll go through 6 unknowns, and the diagnostic properties are in the next slide as well as in the chat, just as reminders for you. And we'll watch the videos together, and then we'll switch into breakout rooms where you can try and determine which mineral is which, and then we'll rejoin in 15 minutes or so. All right, so these are the properties of pyrite. Its color is light yellow. It's not bireflectant, so it doesn't change when we rotate the stage in plain polarized light. And it is isotropic, so it's dark in cross polarized light. The next mineral we'll look at the next mineral that might be there is galena, and it's light gray. It's not bireflectant, and so it doesn't change when we rotate the stage in plain polarized light. It's isotropic, so again, it's dark and cross-polarized light. As an extra identifying feature is that there's little triangular pits form on the surface, and that's because it's really soft. So when we polish it, it pulls out little bits of the galena and they make triangles. Also, somewhere in these videos is going to be arsenopyrite. So it's light gray and sometimes with a pinkish tint. It is bireflectant, but this is a pretty subtle in the samples that I have at least, where there's a very subtle change from like pinkish gray to just gray when you rotate it in plain polarized light. And it's anisotropic, and it goes from dark gray to kind of bluish. Another mineral that might be here is sphalerite. Its color is gray. It's not bireflectant, so it doesn't change color when rotated in plain polarized light. It's isotropic, so it's dark in cross-polarized light, but it actually has another identifying feature. So it's got internal reflections. So there's kind of sporadic yellow to red glow in cross-polarized light. So it might look kind of tricky into thinking it's anisotropic because it's got these internal reflections. But hopefully you'll be able to figure out which one this one is. We'll also have somewhere in the next set of videos molybdenite, which is going to be light gray. And it is bireflectant, and it goes from gray to white when rotated in plain polarized light. And it's anisotropic, so it has strong gray tones in cross-polarized light. And then we're going to look at, also on here is going to be magnetite, which is gray with some pinkish tint. It is not bireflectant, so it does not change color when rotated in plain polarized light, and it's isotropic, so it's dark in cross-polarized light. So you might have noted that a number of these minerals are gray, and it's because I kind of want to highlight how we use the other properties, like whether it's anisotropic or bireflectant to identify the minerals. So the list of samples I went through before are going to be in these videos somewhere, but not necessarily in the order that we went through. So I think you should probably open up that file so you can look back onto the other minerals as we go through the videos and just jot down for each sample what the color is, whether it's bireflectant and whether it's anisotropic and what colors are associated with that. And then you can hopefully in your groups work through what samples you think the different videos are. So we'll just go through the videos now. All right, so this is sample 1. We're rotating the sample in plain polarized light now. Right now we're switching to cross-polarized light. Now we're on to sample 2, plain polarized light. And now we're in cross-polarized light on sample 2. And now we're in plain polarized light on sample 3. Now we're cross-polarized light on sample 3. And here we are, plane polarized light on sample 4. And here we are in cross polarized light on sample 4. And here we are, plane polarized light on sample 5. Here we are, cross polarized light on sample 5. And here we are, plane polarized light on sample 6. Sorry for the typo there. Here we are in cross polarized light on sample 6. Okay, so now we're going to send you off to the breakout groups. We'll give you 15 minutes to discuss the videos and try and identify the different minerals. And then we'll come back and we'll discuss the results. And there's a file that has the identifying criteria that I went through a few slides ago in the chat. So maybe click on that, just download it, as well as there's a link to the different YouTube videos of the different unknowns. And these should be timestamped so you can go to the different ones if you want to just double check on that. And yeah, good luck, and we'll see you in 15 minutes.